Hello, this is my Physics 2211 video on Lab 4, Oscillation. In this lab, our purpose is to analyze the motion of an oscillating mass on a spring, which we're given an MPOR video of, and we use Tracker to analyze, constructing a model to represent the motion of the oscillation using GlowScript, comparing the predicted model to the real motion of the oscillating object, and analyzing the changes in energy of the motion. Now, to go beyond, this lab helps us both to understand the energy and the forces that go along with an oscillating object. Now we move to Tracker, which will show the video of oscillating mass. As you can see, I calculated the origin at this point, at the fixed attachment point for the spring, and then the length of this, the spring at rest being 0.7. Now, as you can see with the object, I plotted the mass of said object as it oscillates around this object, and the data for the spring is given here with time, x distance, and y distance, and graphed up here with the x distance and the y distance as it oscillates over this given period of time. And now I'll move on to the initial values given based on the track. Initial values, we're given the ball's mass, the gravitational constant, and the initial velocity as it starts from rest from the given data on before we start Tracker. And the calculated values, we get the initial position based on the 0 time scale from Tracker with x position and y position. Then we get spring constants, which will show the calculations based on the initial position, L0 spring length, which will show the calculations, and period and the x, which I used, and I'll show the calculations at the very end. From the calculations of the initial values based on our Tracker data, we first need to get the calculation of the spring constant, which we use the manipulation of the period formula to get to the spring constant, which we calculate the period before, which I'll show you at the end of the video as it pertains to a what does it mean question. Then, for the calculation of L0, we find that the average F gravitational force is equal to the average F spring force, with the oscillating object moving between the two. Then we have mg equal to L minus L0 times k constant, get that to L0, and then we find L0. The fundamental physics principles that we apply in this lab, we have the energy formulas with kinetic energy, potential energy, and spring energy, and then the energy conservation formula where the change in energy is consistent throughout the entire system or remains the same. We have the force formulas with Fg and F spring, right there, Fg and then F spring, and then you have the spring oscillation formula, T, which we manipulate to get to the spring constant. Apply Newton's second law, F net equal times ma, or an object will accelerate in the direction of the net force on the object system with the summation of forces from the surroundings on the object making the net force. To our GlowScript data with some of the results of the GlowScript data shown. The coding makes, you can see here, we have the visualization graph information, which is shown here, which is given. Then we put in the initial properties and initial conditions with the ball's mass, initial position, initial velocity, and t and delta t for time. Then we have the gravitational constant, spring constant, L naught, and then we have the calculations of L hat, and spring displacement, which is spring length and spring direction. Then the energy formulas over here with kinetic, potential gravitational, potential spring, and then the E, conservation of energy. Then we have the while loop, which is the calculation loop, calculating energy, gravitational, spring, opposing, and F net, velocity update, position update, calculations for spring length, direction, and displacement. And then we have the energy formulas again to update them. And then when we run the program, as shown right here, we can see the model of the energy graph over here. And now, as to save time, we'll shift over to show the data again in the initial slides, which I showed just before. You can see this is my resultant thing where I based it on the x-axis versus the y, and they changed the energy graph over here. Then, as the analysis, we can say that the motion model is very close to the actual value in the y direction, with the only real change being the timing is off, and the real motion having a shorter period than the length, and a little smaller terms than the distance oscillating for the motion in the x direction. The period for was real quicker like before, but the distance oscillating was much closer in the y direction, and the period is a lot closer to the model than the real model, which is based on an period for the x rather than the y period. Now, when comparing energy values, at any point on the graph, the energies will add up to 0, with the energy and the line being suddenly energy equaling 0, as shown in the yellow line over here. There is an opposite difference in the gravitational potential and spring potential, but acting opposite with each other, with the peaks and troughs being opposite in the graph, and kinetic acting at double time in comparison to the energies of the potential, being the kinetic energy being in blue, the gravitational being in red, and the spring being in green. In conclusion, for some of the improvements I can make on the data, in terms of Tracker, I could have better calculated the masses and been more accurate with the data. And for coding, I could have implemented something that could have utilized a better updating position in order for it to be a lot smoother with the real-time versus predicted motion of the oscillating spring. And I could also use the period in the y to make it look more accurate in the y direction rather than the x. For the what does it mean statements, is the energy principle satisfied? I would say yes. As seen in the section of the oscillating spring in the graph, we can see that the interaction with the surroundings, as it is a closed system, so we can note that the gravitational kinetic energy, gravitational potential, and spring potential, which all end up equaling 0 for the entirety of it, as that arrow is represented by the orange line and stays 0 the entire time. For the what does it mean statement, we can use the data and estimate both the period of the x and the y, and then we can compare the two. Now, first, we take the amount of revolutions in the waves and take the average amount of time it takes, divide them by each other, and then we get the period for said in the x and the y. Now, we take 1, 2, 3, 4, 5 revolutions divided by around 8.14 seconds, and we can get in the period in the x direction to be 1.64 seconds. Now, when comparing the two periods, the y period is much smaller than the x period, showing that the mass oscillates faster than the y, showing that it's more erratic in the y, and that doesn't appear smooth in a consistent line that doesn't change throughout the motion. Thank you.